Hi everyone, this is Mr. Hall and this is a really quick video on chemical cells and batteries. It's part of the separate science chemistry content of AQA GCSE. This content's kind of in the spec. It's with 4.5, which is energetics, which seems a bit unusual because, to be honest, it's probably got more in common with the redox and electrolysis stuff that you did in the previous unit on chemical changes. All right, so if you've done that unit and you've done it well and it's fresh in your head, this will hopefully make a bit more sense to you. In terms of the stuff that we're going to go through in this video, we're going to go through the factors that affect the voltage of a cell. We're going to describe the differences between rechargeable and non-rechargeable cells. We're going to interpret data on chemical cells. And then finally, we're going to evaluate the use of chemical cells. I'll be touching very lightly on the final one, evaluate. I'll be focusing a lot more about the science of how these chemical cells actually work. Now, what you've done beforehand with electrolysis, particularly of aqueous solutions, is something that looks a little bit like this. So you had an electrolyte, which was sort of in the middle here. So this is your electrolyte. Okay, and then you had two graphite electrodes. Ignore the letters here for now. But you had two graphite electrodes which were stuck into this electrolyte, and then you had a sort of battery here which would connect the whole thing up, and then a current would flow, and then the electrolyte solution would split. Okay, then you'd make different products depending on what you had in there. Now this is a bit different. In a chemical cell, what you have is instead of graphite electrodes, you've got electrodes which are made actually by metals themselves. So in this particular example, I've got a zinc electrode over here, and I've got a copper electrode over here. The important thing about this is that there's a difference in the reactivity of those electrodes. And the most reactive electrode, or metal if you like, we always sort of write on the right. So it's least reactive to most reactive. I'll write that down. So this is the least reactive, and this is the most reactive, and that's quite important to understand what happens with electrons in this whole process. Now, this is a chemical cell as an example, and as you can see, I've connected the two different metals with an electrolyte, and it's connected in the circuit in order to make a current flow. Now, in this cell, as with any other cell, it contains chemicals which react to produce electricity, and this reaction is spontaneous. Now, this is very different to what you've done with electrolysis, because electrolysis was not spontaneous. You had to put energy into it in order to actually split the whole thing up. In this, you don't need to put electricity into it because it's spontaneous. It does it automatically, and that's a very, very important point. Instead of having a cell or a battery, you can see that I've got a voltmeter here. You tend to do that in experiments when you do this in the lab, and then you can see the difference in voltage between two different metals, which is quite interesting, and that's kind of what you pursue when you do A-level. All right, so that's what it is. Now, what we're going to do is we're going to focus on the two different electrodes, the zinc and copper one, just to understand what's going on at each one. So if we start with this one over here, so as you can see here, this is copper, this is zinc. Let's focus on this zinc electrode. Now at the moment, you've got zinc atoms which form that electrode. Now at this electrode, you've got oxidation. So what happens is those zinc atoms are going to lose electrons, and they're going to give it to the electrode like so. Okay, so this atom is going to lose its electrons here, and the same is going to happen to the zinc atom on the right. And as a result, they turn from zinc atoms into zinc ions, okay, missing two electrons, and then eventually those electrons are going to move over there, and these zinc ions are going to fall into solution. So what you've got happening there is oxidation, and the half equation is as so that you started with zinc atoms and then you turn into zinc ions with the two electrons moving to the other electrode. Okay, that's what you've got happening there. Now, it's always the more reactive metal that does this, and that kind of makes sense because it's the more reactive metal that has the greatest tendency to form positive ions. That's a really important thing that you learned previously in the course, and you always got to bear that in mind for this whole thing. Now, if we look at the other electrode, we've got the copper ions over here. Now, the copper ions are part of the electrode. In this particular case with copper sulfate, they'll naturally be in solution too, which is quite useful. So you've got copper ions here, and what happens is you've got the electrons joining like so, and there you have it, and then they will eventually form copper metal. And what you'll literally see is that copper metal building on the outside of your electrode. It will get bigger and bigger and bigger. So, sorry, just to go before I go any further, the half equation for this is, as you can see at the bottom here, where you've got Cu2 plus, which is your copper ion, and that has the two electrons which are donated by the zinc, and that forms copper metal. Okay, so that's that half equation. Now, in terms of sort of the whole thing, these tend to be the kind of cells that you get in non-rechargeable cells. So in non-rechargeable cells and batteries, the chemical reaction basically stops if you run out of something. So if I run out of copper ions, the whole reaction stops. If this zinc gets so small that it can't actually do the chemical reaction anymore, the reaction stops. So it does have sort of a shelf life. It's not going to last forever. Now, alkaline batteries, which are kind of batteries you probably get in the shops, are non-rechargeable. So if you think of like a Duracell 4-pack of AA's, they don't last forever. And the reason why they don't last forever is because you basically use up either one of the ions or you use up one of the electrodes in that reaction and then it stops, okay? And it's non-rechargeable, so you have to chuck them away. One of the benefits of that is, well, it's not a real big benefit, but you have to throw them away. And by throwing them away, obviously you add to landfill and it's a bit of a waste and all the rest of it. But they can be quite cheap and they can be quite convenient, I suppose, in terms of their pros and cons. Now, a rechargeable battery, you can get those. Now, the reason why some batteries are rechargeable is because you can reverse the reaction. To reverse the reaction, that means you have to put energy into it because it's non-spontaneous. So I have to replace my voltmeter with a cell or a battery like so. So if you think about it, batteries such as what you can see here, you tend to have to put them in some kind of plastic contraption and put them in the plug socket, and after a few minutes it will charge. The reason it does that is because you're giving it energy to reverse the reaction. So suddenly you're going to have more of the electrolyte in solution. Maybe it's that which has run out, or you might have to replenish something to do with the electrode. So it's one of those things which tends to get replenished to allow the reaction to happen again. So as you remember from before, there were two half equations we had. At the zinc electrode, we had the top one here, and at the copper one, we had this one here. Now, what you can do is you could combine these half equations or these ionic equations to form just one equation to understand what's going on in the battery. You'll notice there are two electrons in each equation. So what you can do, similar to maths, is you can form a simultaneous equation and you can cancel them out in order to combine those equations. So what you've got is as follows. This can cancel and this can cancel, and then you can bring the whole thing together. So what you have is Zn plus Cu2 plus, which is what I had on the reactant side for both of these, reacting to form Zn2 plus and Cu, which is over here. So effectively what you've got is simply two electrons moving from my zinc all the way to my copper. And the zinc is getting oxidized because it loses those electrons, and my copper ion is going to get reduced because it's gaining those electrons. So this is a really good example of what we call a redox reaction. Remember, redox reaction is one of those reactions where you have reduction and oxidation happening at the same time. So there are a couple of things which can affect the voltage you produce. Now, one of the things, and it's probably the most important one, is the type of electrode. Now, this is a reactivity series of metals. Remember, you need a difference of reactivity in order to produce a voltage. In the example I gave you copper and zinc, and that'll give you a reasonable voltage. Now, what you could do is if I used metals which were closer together, let's say I did copper and lead, that would give me a smaller voltage, okay? But if I choose a much bigger one, let's say I do platinum and magnesium, that will give me a much bigger voltage. So just to put it, kind of summarize, the bigger the difference in reactivity, the greater the voltage you are going to get. There's a couple of other things you can do as well. You can change the electrolyte. Different electrolytes can affect the voltage you get in different ways. You don't need to know how, you just need to appreciate that it does. And then finally, you can change the number of cells. Now, what I showed you in one picture, and you can kind of do this in a beaker or like a battery, that is the example of one cell. Now, if you have lots of cells working together in a series, like in a series circuit, your voltage is going to get much greater, okay? And that kind of makes sense. If you think about a device where you put more batteries in it, in order to make it work, the more batteries you've got, the more juice it has in order to function, i.e. the greater the voltage. And that's it. So I hope that's been useful, and best of luck with your learning of this quite tricky topic.